Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about some popular continuous distributions, in particular the exponential and the Gaussian distributions. The motivation is similar to when we discussed parametric models for discrete random variables. We have already explained how to estimate probability densities for continuous random variables using the histogram and kernel density estimation. These are non-parametric estimators that don't really assume anything about the distribution of the random variable, except that maybe you have certain smoothness, certain local smoothness in the density. Because of this lack of assumptions, these estimates can often be quite noisy, especially if you have limited data. An alternative approach that can help us address this issue in some cases is making some assumptions about the data generating process and using those assumptions to decide on a predefined shape for the distribution that only depends on a small number of parameters that we can then fit using data. This is exactly the same idea as we used when we were fitting discrete distributions to data, except that in that case we were fitting the probability mass function. Here we will be fitting the probability density function. But before we learn how to fit that a probability density function to data, we need to get to know some popular continuous distributions that we might want to fit data to, and that's the goal of this video. So here we're going to introduce the exponential and the Gaussian distributions, and we're going to describe some of their properties. The prerequisites are conditional probability, especially for the exponential part, continuous random variables, and the probability density function. Okay, so now we're going to derive the exponential distribution, and we're going to do it using an example that is very similar to the one we use for the Poisson distribution, which is not a coincidence. These two distributions are very related. Our goal is going to be to model the time until the next earthquake. So we're at time t equals 0, and now we want to see what's the distribution of the time until there's a new earthquake. You can see that it's quite natural to model that time as continuous. In order to compare it to the Poisson case, in the Poisson case, what we're doing is we're saying, oh, imagine now there's 1 year. How many earthquakes are there going to be in 1 year? Okay, so that was a discrete distribution. The random variable there represented the number of earthquakes. This is a little bit different. This is kind of the time between the earthquakes. So now there just has been an earthquake at time 0. How much time until there's another one? Okay, that's the idea. When we derived the Poisson distribution, we made this assumption that the probability of an earthquake in a period of a very small length epsilon was equal to lambda epsilon, where lambda is the rate parameter that essentially tells you how often there are earthquakes, intuitively speaking. So here we're going to make exactly the same assumption. When we focus on the time up until the next earthquake, this assumption means that for any time t, okay, so for any time t, if we assume that there hasn't been any earthquakes up to time t, the probability that the earthquake occurs between time t and t plus epsilon is lambda epsilon. And we can make this mathematically precise using the concept of conditional probability. What we are saying is that conditioned on the random variable t that represents, this is the random variable t, that represents the time of the next earthquake, conditioned on that variable being greater than some fixed constant t, then the probability that we get an earthquake between t and t plus epsilon is equal to lambda epsilon. Okay, this is a precise mathematical formulation of this assumption. Okay, so now let's see what the implications of the assumption are. If we just use the definition of conditional probability, it's equal to the probability of the intersection of these two events divided by the probability of the event that we're conditioning on. The intersection is just equal to this event, if you realize, because this event is included in this one. And we can easily compute it using CDFs, right? So this intersection is just the probability that the random variable is between t and t plus epsilon, and that is just equal to the CDF at t plus epsilon minus the CDF at t. And down here, this is just the probability that the random variable is greater than t. This is just 1 minus the CDF. Okay, so we have an expression in terms of CDFs. This is the expression that is going to be equal to lambda epsilon. For our derivations, it's going to be easier to deal with 1 minus the CDF. You can see it there in the denominator. This is called the survival function in the statistical literature. It's not too important what it's called. This is just, in this case, this is just for convenience of notation. So we have this equality, okay? St minus St plus epsilon divided by St is equal to lambda epsilon when epsilon is very, very small. So now we're going to move things around a little bit and we get this equality, and we're going to take the limit where epsilon goes to 0. We have S of t plus epsilon minus S of t divided by epsilon when epsilon goes to 0. This should ring a bell. This is just the definition of the derivative. Okay, so we have that the derivative of the survival function divided by the survival function is equal to minus lambda. If you remember by calculus, this is exactly the derivative of the logarithm of S of t, okay, because the derivative of the logarithm of x is 1 over x. So now we can integrate on both sides. If we integrate on both sides, we're going to get minus lambda t plus some constant k is equal to log of S of t. And now we can take exponentials, and we're going to get that exponential of k exponential of minus lambda t is going to be equal to S of t. And we're going to call this some constant c. Okay, this is just basic calculus. We have found that a consequence of the assumption that we made is that the survival function is an exponential, which means that the CDF is 1 minus an exponential. Okay, now we have to figure out what's up with this constant here. But the thing is that, remember that we're considering the random variable as starting from time 0. So we're going to assume that it cannot be smaller than 0, which means that the CDF at 0, should equal 0. Okay, the CDF at 0 is 1 minus c, right? Because if you plug in 0 here, you get a 1. So this means that c should be equal to 1. So after all of this calculus, we end up concluding that an implication of the assumption that we have made is that the CDF is equal to 1 minus exponential of lambda t. If we differentiate this, we get that the PDF is equal to lambda exponential of minus lambda t, and that is the PDF of the exponential distribution. This is where it comes from that assumption. The PDF of an exponential random variable with parameter lambda, which is this rate at which the earthquakes occur, or whatever phenomenon we're modeling with the exponential distribution. And exponential distributions are very popular. They're used to model earthquakes, for example. They're used to model neuronal spikes in neuroscience. We will use them now to model inter-arrival times between calls. They're also used to model inter-arrival times between emails, etc. The PDF of the exponential looks like this. It's lambda e minus lambda t for t greater than 0, and it's 0 otherwise. How does it look like? It looks like this. For lambda equals to 0.5, as we increase lambda, it decays faster. This lambda equals 1, lambda equals 1.5, and you can check that this integrates to 1. So it's a valid PDF. Okay, so now let's take a look at what happens when we apply this on real data. We will talk about exactly how we do this, how we fit the parameter to the real data in the next video. But first, let's just look how it works. We're going to model the time between calls in the call center that we already considered in our example on the Poisson model. And we're modeling, again, like the inter-arrival times between calls for calls that are between 6 a.m. and 7 a.m. on weekdays. We have a training data that are calls from January and June 1999, and a test set that are calls from July to December. So what we're going to do is we're going to use a non-parametric density estimator based on kernel density estimation, and we're going to compare it to fitting an exponential. This is what the kernel density estimate looks like. It's a little bit noisy, but it adapts reasonably well to the shape of the test data. So I'm showing you here a superposition of the histogram of the test data with the kernel density estimate on top. It's pretty good. It overshoots the test density for very short inter-arrival times, indicating that in the training data there are many more short inter-arrival times when compared to the test data, and this can just be because there's different months in the training data and the test data. As in the case of discrete, when we were talking about comparing discrete parametric and non-parametric models, you have to be a little bit careful what you call overfitting. This, in this case, might be overfitting, or it might just be that there's this systematic difference between the training and the test set, and if we had tested it on a training set that also included the same kinds of months, so January to June, for example, in the following year, it might actually have performed well. This is just so that you can see how it's actually very tricky to define a good test set. In this case, we only have data from January to December. Okay, when we look at the exponential model, in general, it adapts very well to the data, but it undershoots the number of short calls. This seems to indicate that, not short calls, sorry, the number of short inter-arrival times between calls. This seems to indicate that there might be some more structure to the data that is not taking into account in the exponential model. It seems that there's a tendency of there being more short calls than you would expect from something that is actually exponentially distributed. But from the rest, we do see that the exponential density gives you a pretty good fit to the test data. So as usual, the parametric model is pretty good, but it's not perfect because there is some structure that it cannot, that is not accounted for in the assumptions that we have made to derive the parametric model. Okay, now let's talk about conditional probabilities, because the exponential distribution has a very interesting behavior when you consider its conditional distribution. So let's think about how the inter-arrival times are distributed if we only consider times that are above a certain number t0. Okay, like 25 seconds, 50 seconds, and so on. We'll look at them in a moment. We are interested in how the distribution changes. So we're going to look at calls between 9 and 10 a.m. The only reason why I've changed the time of the calls is so that we would have a higher volume of calls, because when you're conditioning, we already saw this when we're talking about Monte Carlo estimation, when you condition, it's very easy to end up without data. You'll see what I mean in a moment. Okay, so first we're just looking at the histogram of inter-arrival calls in the same dataset, the call center dataset, starting at the beginning. Okay, this is just a histogram of all the calls between 9 and 10 a.m. And this is the kernel density estimate corresponding to that histogram. It looks exponential, as we were talking about fitting an exponential to this earlier on, so it looks pretty exponential. Now we're going to look at the histogram starting at 25 seconds. So we only consider calls that are inter-arrival times between calls. That's complicated. That are longer than 25 seconds, okay? So the random variable t greater than t0, which is equal to 25 seconds. So essentially we have truncated the histogram and only considered values greater than 25. Interestingly, when we renormalize the kernel density estimate, it still looks exponential, except that now it starts at 25. Interesting. Let's do that again for 50. Of course, we have less and less data. This is why I was saying that I needed a higher volume of calls in order to be able to do this experiment. Now we renormalize again. Boom. Kind of exponential starting at 50. Interesting. We do the same for 75. We're almost running out. So the kernel density estimator is quite noisy, but still, you know, it looks pretty similar, but shifted to 75. And now I'm going to put them all on top of each other, shifting them all down to the origin, all of these conditional densities, and it turns out that they're extremely similar in the real data. So this seems to indicate that, to a first approximation, the distribution of the time that you have to wait for another call to come in if you have already waited until time t0 is actually very similar to the time at the beginning. This is like when I call the DMV and I'm waiting there for an hour listening to the stupid music, and I ask myself, how long am I going to have to wait more? Like, am I going to have to wait less because of having waited for an hour? I suspect not. If the waiting times at the DMV are exponentially distributed, then I'm completely right. Okay, I have the same distribution of time until someone picks up the phone as at the beginning, which is definitely the feeling that I get. Of course, on real data, this is not exactly true because eventually, you know, we run out of data. Like if we continue truncating the histogram here, it's unclear what we're going to see. Okay, but let's see for an idealized exponential model if this property actually holds. So what we're interested in is the probability, so not the probability, the distribution of this random variable t when we condition on t being greater than a certain fixed value t0. By definition, when we're going to define the conditional CDF conditioned on this event as the probability that t is smaller than any particular value, conditioned on t being greater than t0. By definition, this is the probability that t is between t0 and t, the intersection of those two events, divided by the probability of what we're conditioning on. If we can write this in terms of CDFs very easily, CDF of t minus CDF at t0, sorry for the small typo, divided by 1 minus the CDF at t0. Okay, and here I'm going to have the same typo again, so there we go. When we use the fact that, remember, the CDF of an exponential is 1 minus e of minus lambda t, and remember, just to make sure I explain what's happening, we saw in the real data that these conditional distributions seem to all be kind of the same. Now we're going to prove it for this idealized exponential model. So that's why we're looking at this probability of t is more equal to t conditioned on that. We end up with this expression. When we divide, we get 1 minus exponential of lambda t minus t0, which, if you realize, is just the CDF shifted to t0. And when I differentiate, I get exactly the exponential PDF shifted. I'm going to do this one last time, shifted to t0. Okay, that's what I get, which exactly matches what we observe on the real data. So this proves that if you have an exponential distribution and you say, okay, so now what's the distribution if the random variable is greater than any particular value, it stays exponential. Let me give you this property is called the Memoryless property, and it actually, as we saw, you can actually see it approximately in practice on real data when data are approximately exponentially distributed. This is a graphical explanation. If you look at the exponential PDF and now you truncate it at a particular value here at 2, if you renormalize it, boom, you get another exponential that starts at 2. Okay, so that's a really like 2-second graphical explanation of what we just proved. Okay, so now let's move on to the other famous distribution that we're going to cover today, which is the Gaussian distribution. The motivation to use the Gaussian distribution is that when we have a sum of independent quantities, this is often approximately Gaussian. We're going to talk a lot more about this later on. This follows from the central limit theorem. For now, I'm just going to show you what the parametric PDF of the Gaussian looks like. It has a certain mean and a certain standard deviation sigma. It looks like this. It's like a squared, like exponential of a squared. the PDF is centered at mu, so here mu is equal to 3, so the PDF is centered at mu, which is called the mean. We'll see that the mean of a random variable actually means something very precise a little bit later on in the course. And sigma is the standard deviation, which basically tells you how fat or how thin the density function is. We will also define the standard deviation more precisely later on in the course. This is an example where mu is equal to 3 and sigma is equal to 1. If we make sigma larger, we make the density fatter, and mu just shifts it. So here it's centered at -2. Here it's centered at 0, and it's really fat because sigma is equal to 4. Okay, so an important property of Gaussians is that when we multiply them by a constant and we add a constant to them, they remain Gaussian. So here by a standard Gaussian, I just mean a Gaussian where mu is equal to 0 and sigma is equal to 1. So now we're going to see what is the PDF of sigma a plus mu. For some special values of sigma, so for some arbitrary values of sigma and mu. I realize that this is a bit confusing, so I'm going to erase this. A standard Gaussian is a Gaussian where the mean is 0 and sigma is 1. So basically the PDF is equal to 1 over square root of p exponential of minus a squared over 2. Okay? That's the PDF. You can probably hear a motorcycle out of my window. Let's just move on. Okay, so what is the PDF of sigma a plus mu? We do what we always do. We say, okay, I want to derive the PDF, but it's the CDF that actually has a meaning in terms of probabilities. It's a probability that b is smaller than this specific value, and b is defined as sigma a plus mu. Now I know the distribution of a, which is the standard Gaussian, so I can just compute that by integrating, right? Well, first I move mu to the other side, sigma to the other side to obtain this. And now I just need to integrate from minus infinity to this. I have an expression for the CDF. What I really want is the PDF. So I differentiate with respect to this. Remember that when we differentiate a function like this with respect to x, this is just equal to f of x. Let's call this g. This is just equal to g of x. Okay, this is just basic calculus. So now the derivative of this is going to be this, and now I'm also going to have to take the derivative of that, like by the chain rule. So what I have is that the derivative is equal to this function plugging in this value times the derivative of this with respect to b. We're taking the derivative with respect to b because that is the argument of the CDF. This means that when you take a Gaussian for which sigma is equal to 1 and mu is equal to 0, and you multiply by some constant and you add another constant, the multiplicative constant becomes the sigma parameter. Okay, you get a Gaussian that has that multiplicative constant as a sigma parameter, and you shift the distribution to mu. Okay, so now I want to show you something which is, I used to show this example to explain, to just demonstrate how well Gaussian distributions fit real data, and I think it's a very instructive example. Okay, so I went to this data set, like from UCLA, I think. They have a lot of public data sets, and I mean, they do a great job. And they had this human weights and heights and weights data set, so I used it for my course. I plotted the histogram and fit a Gaussian to it, and I was like, wow, this is the best example ever. Like, look at this amazing fit. The power of the Gaussian, amazing. And this year, I went back to the datasets because I was redoing I was trying to put the Python notebooks online and so on. And what I realized is that the data were simulated using a Gaussian distribution. So, be careful. Be careful when you take a look at data out there, because you might be fooled into thinking that parametric distributions are better than they actually are. I have now found a real data set of heights, which we use in previous examples from the US Army. And when I fit a Gaussian to it, it's actually really, really good. It's not perfect. So I don't know if you remember, you can take a look at the video on the histogram and kernel density estimation, but there is a certain asymmetry. This part is higher than this part, and that's not accounted for by the Gaussian. But otherwise, the fit is still pretty good for this dataset, which is actually real. Okay, so what have we learned? We have derived the exponential distribution, and we have described several properties of the exponential and Gaussian distributions. And then we have seen that they fit real data pretty well. Thank you very much.